And it sits there, and one of the things, if the glycocalyx actually can stop viruses getting into cells, it can block them from getting into cells. So people who have damaged glycocalyx are more likely to have viral infections. So diabetes damages your glycocalyx, and diabetes increases your risk of COVID, and it all adds together. But they never heard of the glycocalyx. I mean, like almost everything about the endothelial cell, they were thought to be like wall tiles or something initially.
Yeah.
They just sat there and kind of acted as a barrier, and that was it. They're probably, in fact, they're probably the most complicated cells in your body.
Right.
And they just, this idea that they would just, oh, look, here comes an LDL molecule. Well, I tell you what, I'll just let it go straight through me and into the artery wall. Or I tell you what, I'll just let it go straight past me and another cell and into the artery wall. And I'm only going to do this in certain parts of the artery wall because why? Huge sums of money. I mean, you lower cholesterol.
That's right.
Statins have made $1 trillion, possibly, with profit. There's new cholesterol lowering, LDL lowering agents coming out all the time, and they get promoted hugely. And then there's the entire low fat, saturated fat industry that make more trillions by selling rubbish, low fat, high carb foods to people and make vast sums of money out of it. So there's definitely that. Anyway, you eat too much saturated fat, and it's gunky stuff.
Clogs up your
gunky
arteries.
Stuff gets into your bloodstream and gunks up your arteries.
Yeah.
In some gunky way that actually makes no scientific sense whatsoever. It does not mean. I mean, I tell you what happens when you eat saturated fat or any fat is it goes into your, obviously, into your small bowel. Bile, which is cholesterol, comes and links to it. Otherwise, the body can't absorb it. The bile links to the fats. It's absorbed into your small bowel. It's put into a really big lipoprotein called a chylomicron, which is maybe the size of a beach ball if an LDL is the size of a tennis ball. This then is delivered straight into your bloodstream through a thing called the thoracic duct. And the thoracic, then it goes around the body, losing all the fat, and then it shrinks down and down and down and down and down until it becomes about the size of an LDL molecule, at which point it's absorbed into the liver, broken down, and it's gone. That's what happens to fat. It's really simple, right? And that has nothing to do. It's like, where's the connection with LDL there? There isn't any. Yeah, you're right. There isn't any. There is no connection whatsoever.
Yeah.
It has nothing to do with the LDL. So how is VLDL made? Well, if you eat carbohydrates, they are transported directly into your liver, right? All of them. They are turned in basically into fructose and glucose just about entirely. Simple sugars. They go into your liver, and if your liver is full of fructose, is then turned into glucose because your body doesn't like fructose very much. Once your liver is full of glucose, it turns it into glycogen, which is just lots of glucose molecules all stuck together, a bit like starch. And once your liver is full of glucose and glycogen and it can't take any more, it says, what am I going to do with it? And what it does with it is it turns it into fat.
Right.
It transfers it into fat, and it makes it into fat. It's called lipogenesis. Lipofatogenesis, to create. Lipogenesis comes from sugars. Sugar. So if you eat carbohydrate, it goes into your liver, and once your liver's full, and once your muscles are full, and you can store about 1,500 calories that way, ish. At that point, your body has no choice. It turns it all into fat, all right? And it turns it into fat, and it sticks it into a VLDL molecule along with cholesterol and pops it out. And then the fat in the VLDL is got rid of until it turns into an LDL. And then once 99% of LDL is just reabsorbed into the liver, where it's broken down and reutilized again. So you say, well, what makes VLDL go up? Well, what makes VLDL go up is eating too many carbohydrates. I remember discussing this with a professor of biochemistry. I was having is the English breakfast good for you argument. I said to him, well, if you eat too many carbohydrates, it's converted into fat. The fat is converted into VLDLs, triglycerides. The triglycerides go around your body, losing their fat, and they're turned into LDLs. LDL goes back into your liver, where it's reused. The various proteins and things it needs are reused. And he said, how do you know that? I went, well, I read it. I said, and I spoke to people. And he didn't seem to know that this was the case. So I was looking at him thinking, you're a professor of lipidology. Anyway, but it's almost like he couldn't say this, because once you start saying this to people, they go, so if you eat carbohydrates, your LDL must go up. You go, no, it doesn't actually. It's interesting. Your VLDL is here, and the only source of LDL is this. Your VLDL goes here, and your LDL stays rigidly here, all right? What does this tell you, gentle reader? It tells you that the liver can control the level of LDL, and does so, and it does it very easily. And it really makes no difference what your VLDL does to your LDL, because the liver doesn't care. It controls the LDL level. It puts out more receptors, it pulls it in, it takes it in as needed. What does this tell you? Well, it tells you that some people with familial hypercholesterolemia, which I talked about earlier, where you don't have LDL receptors, and there's a very rare condition where you have both genes, so your LDL is like, if your normal is 3, these have got 30 and 40 or whatever. If you do a liver transplant on these children, the LDL level becomes normal, like that. Just straight like that. You say, well, why is that? It's because the liver controls your LDL level. And it has nothing to do with the amount of saturated fat you eat. Nothing to do with the amount of saturated fat you eat.
Right.
And people say, but if you give people polyunsaturated fats, the LDL level goes down. I said, yes, it does go down. And do you know the reason for that? And they don't, because they don't read anything. Is that polyunsaturated fats and oils have a lot of things called stanols, and you might have heard of stanols and sterols.
Yes, I have. Yeah.
Plant stanols lower your cholesterol. Well, they don't actually lower your cholesterol.
Are you speaking of vegetable oils right now?
Vegetable oils, yes.
Yeah. Okay.
Well, the vegetable oils themselves, but within that are the vegetable stanols, because cholesterol is found in cell membranes, which are what animals have, and in cell walls, which is what plants have. They have a thing called a stanol or a sterol. They're interchangeably used. Now, cholesterol is actually a form of stanol or sterol. It's just that we don't tend to call it that. So if you eat lots of vegetables and stuff, you get a lot of stanols and sterols, and the body absorbs these instead of cholesterol. All right, and then it deals with them differently, and your LDL level drops because of this, because the liver's not getting enough cholesterol. It's getting stanols and sterols. It's not the saturated fat that makes your LDL go up. It's the stanols and sterols and the way they're dealt with in the liver that makes your LDL go down, because the liver's reabsorbing it more rapidly. And you're arguing with me. You've never even heard, you don't even know what a stanol is. You don't know what a VLDL is. You've no idea how saturated fat is dealt with in the body. You don't even know where a LDL molecule comes from. You don't know what it contains. You know nothing about it. And yet you're telling me this is how heart disease works. But actually, if you've got a high VLDL level and a low HDL level, that means you've got insulin resistance.
I see. Yeah.
And you're eating too many carbohydrates.
Right? So looking at your cholesterol is a good indicator of heart disease, but not in the way that people think.
Well, the LDL is the thing that people are focused on, saying that's right, the one that causes heart disease. And go, well, actually, A, it's not cholesterol. Stop calling it cholesterol. It's just stupid. B, it's got nothing to do with the rate of heart disease. Giving you what you call your total cholesterol level. That includes your VLDL, your HDL, and your LDL. Your VLDL level is divided by 5 for reasons unknown to man. Your HDL is calculated, and then what's left is considered to be your LDL. It's called the Friedewald equation. It's horribly inaccurate. You go to 3 laboratories and ask for your total cholesterol, your VLDL, and your HDL, and you'll get a different answer from all of them. Not even within 30%. I'll guarantee I've done it. These are not accurate tests. But yes, if you decide that your total cholesterol is high, if that's made up of high VLDL, you have another problem. It's not the VLDL that's causing you to have heart disease. It's just telling you. This is the argument of yellow fingers and lung cancer, which you may or may not have heard.
No.
People with yellow fingers are more likely to die of lung cancer.
Okay.
Amazingly enough.
Yeah.
Did you not know that? No. Why is this? It's because they smoke. Because that gives you yellow fingers. All right.
So I missed that one.
Yeah. You know, it's a classic epidemiological thing. Anyway. So the question is, when you're looking at it, VLDL is high, people have higher rates of heart disease. Yes. And well, because if you've got insulin resistance and metabolic syndrome, you'll have high VLDL levels. That's the thing that's causing the heart disease, not the VLDL. Yeah. If you've got a low HDL, well, that's another, because actually as VLDL comes out of the liver, HDL comes up to it and swaps like things, other proteins on the surface of them, in order that the VLDL can be recognized by receptors around the body, and therefore the HDL level drops. So the higher your VLDL level goes, automatically the lower your HDL level goes. They're associated levels. And so one goes up, one goes down, the LDL level stays the same, the calculated figure appears to be the same, but you've got a completely different problem going on, if you like. And yet, people have just said, oh, it's cholesterol. A, it's not cholesterol. B, there are different things. And then there's another lipoprotein that no one's even mentioned yet, which is called lipoprotein A. And again, guarantee anyone listening to this, go and ask your doctor what's LPA. They will not know. The LPA is a LDL molecule with a specific protein attached to the side of it called apolipoprotein A. And there's a really interesting whole story about apolipoprotein A, which is to do with the fact that it is highly involved in regulating blood clots. And you cannot find it in animals, or you find hardly any of it in animals that manufacture their own vitamin C. You think, well, where does this story go? Well, vitamin C, all right, this may seem like a side, it comes back around, don't worry, we'll get there in the end. Vitamin C, a lack of vitamin C causes scurvy, right? Nobody knows what scurvy is. But what scurvy is because vitamin C is required for the body to make collagen. You may have heard of collagen.
Yes.
Sharks are made of collagen, not bone. And it's really,
aren't we made of collagen mostly, like fascia, muscles? Are we made of collagen mostly?
Without collagen, we would just be a disintegrated mush, right?
That's right. Yeah.
We'd have bones, but the rest of us would just be mush. But one of the first organs or parts of the body that needs collagen in order to not break down are blood vessels. So if you don't have enough collagen, your blood vessels start to crack. And one of the first signs of scurvy is your gums bleed because your blood vessels are breaking open, right? And then you bleed internally, and then you die of internal bleeding, all right, which is a pretty nasty way to go. And so you can't make vitamin C. Now, there's about 9 animals that can't make their own vitamin C. Guinea pigs, some great apes, some weird things that I can never remember the name of, and us. You think, well, why don't we make vitamin C? It seems silly. It's made from glucose, by the way, and looks almost like a glucose molecule. So if you can't make vitamin C and you don't get vitamin C, your blood vessels start to break down, and then you die of bleeding to death. So the body at some point came up with a patch. It said, if we're breaking down, can we stick things to the side of blood vessels to stop them cracking? And the thing they used is LPA, lipoprotein A. That's the sticky stuff that forms like super glues your artery walls together. But they did some experiments once on guinea pigs who can't make vitamin C, and they got all the vitamin C out of their diet. Then they started to develop atherosclerosis in their blood vessels, which guinea pigs don't normally do. Then they gave them the vitamin C back, and the atherosclerosis disappeared. So the same thing happens in human beings. Now, LPA is one of the lipoproteins, and it is part of the whole measurement, although no one will give you the actual figure unless you ask specifically for it. But it's really important. It is actually the lipoprotein that is important, because when you look at plaques and people say, oh, they've got lots of LDL in them, the answer is no, they don't have lots of LDL in them. What they have is lots of LPA in them. And how would you know the difference? Because the basic structure molecule LDL is exactly the same. The only difference is that LPA has this protein wrapped around it called apolipoprotein A. And if you don't look for that protein, you wouldn't know if it's LDL or LPA. And no one looks for this protein, but some people have looked for this protein, right, including Elspeth Smith, including, unfortunately, Matthias Rath. You know, when they did coronary artery bypass surgery and they take out the old artery and then they look at it and say, look at all these plaques, and they examine them. He examined them and said, so what's in here? Is it LDL or is it LPA? Right. And the only way you can tell is if you look for this stain for this particular apolipoprotein A. And what he found was that, well, there it is. There it is. It's there, and it's there in plaques in high concentrations.
Right.
So what's in plaques is most likely LPA.
Not LDL.
Right? Not LDL. And that would make sense because LPA is designed to plug damaged areas of artery wall. And people with a high LPA level are far more likely to die from heart disease than people with a high LDL level, for instance. But of course, when clots form, LPA, LDL, the whole thing, they all get rammed together inside the clot in quite high concentrations. So there's a part of the argument. The other thing is, years back when they found what they thought was cholesterol in plaques, what they were seeing was cholesterol crystals, right? And you may think, well, where did that come from? That must have come from LDL because that's got cholesterol in them. The answer is, again, it's like everything you look at, you can turn it around and say, no, you've looked at it this way, but actually you're wrong because it's this way. Yeah. Turn it around 180 degrees. The one place a cholesterol crystal cannot come from is an LDL molecule. Because as I said before, cholesterol in LDL is linked to fats as a cholesterol ester. It is not cholesterol. It is cholesterol ester, different chemical. You can't make cholesterol crystals from cholesterol esters. So where does the cholesterol crystals come from? So they're there. I fully accept there's lots of cholesterol crystals in quite a lot of plaques. I say, well, that must have come from LDL because they carry cholesterol around. No, they don't. They carry cholesterol esters around. What carries cholesterol, pure cholesterol around in the body? Where is the only place you can find it? The only place you can find a cholesterol in its pure form is in the membranes of red blood cells. Is because it's really complicated to get oxygen in and CO2 out, and it needs a very, very careful construction of the membrane for this to happen, and that requires pure cholesterol. It's the only place you can find it intercalated. It's got intercalated in between the two parts of the membrane is pure cholesterol, right? So the only place you can get cholesterol crystals from is red blood cells. And what do you find in blood clots in very high concentrations? Is red blood cells. So the only place that cholesterol crystals could have come from inside a plaque, and people find these things, is from red blood cells being incorporated into the blood vessel wall. And the only place that can come from was a blood clot.
Right.
So people have looked at lipoproteins and said, oh, look at all that LDL, wrong, it's LPA. People have looked at the cholesterol crystals and said, oh my God, that must have come from LDL because that's what cholesterol comes from, wrong, they're cholesterol esters. It comes from red blood cells. That's the only place it can come from. And I've read about 20 papers that have said this. All right? They've said this is interesting because this is the only place it can come from. And how much impact has this had on mainstream thinking about blood, about plaques and cholesterol? None. And yet they'll still say, oh, well, plaques are made of cholesterol.